Howdy folks, I'm Keith Bowen and this is Hard Rock University. Today's lesson is on classification and how you use it in conjunction with gravity separations to improve your recovery. Classification can be done many ways. It basically means sorting by particle size. However, the most common way and the way we're going to be using that in this lesson is through the use of a screen. You actually have something with holes in it that something goes through and something is rejected off of. That's the process of classifying. Now, we're going to use a little chart here and a little graph, not much math, and it's going to be a little odd, but there's a reason for it. Okay, now, this axis here is particle size. We'll start with big particles here, medium particles here, small particles here. Okay? This is particle size. This one is going to be settling velocity. And that means, literally, the speed at which the particle settles in water. And they've measured these things. There's lots of equations and everything else. Again, it's up here. Doesn't matter. What matters is, in reality, how does your process work with your ore? So, the one thing I'm going to do strange here, though, is I'm going to have a small settling velocity up here and a large settling velocity here. So this means slow settling, and this is fast settling. So, settling velocity depends on the density of the material, the shape of the material, and the size of the material. We'll start here with gold. Let's say we have a large gold particle here. It's dense, it's large, it's going to settle fast. I'm assuming for today's lesson, to make things simple, they're all the same shape. Okay? That's not reality for you, but for now that'll do. And a smaller particle will settle slower. And a real small particle will settle slower yet. So, you can draw a graph, a curve, through this, and you can determine what the settling velocity of all the different particle sizes are. Now, this is for gold. So let's suppose we now have pyrite or magnetites and black sands, whatever. We've got some other material of an intermediate density between the normal quartz and feldspar and gold. I'm going to call it pyrite, because I deal with hard rock and you're more likely to have pyrite. Now, a same size pyrite particle will settle slower than a gold particle. Same for medium, same for small. It's going to have a curve something like that. Silica, quartz, feldspars, things like that, your common minerals that are worthless, are going to be like up here. And they're going to have a curve like that. Now the reason I drew these axes like this is, let's suppose you had these three particles up here, these three particles up here, these three particles together up here. This was water, and you let them go all at the same time, and then at a particular time you took a picture. This is where the particles would be in that water column. This is what happens when you actually are running a water column. This is where they're going to do. They're going to settle at these rates. Now, a gravity extraction can depend on other things besides settling velocities and shapes, and, but they all work together. So a higher settling velocity is going to get easier trapped than a lower settling velocity, period. There may be other reasons for that, but that's what happens. Like if you change the mat in your sluice box, it's, you know, there's little vortices and stuff like that that come into play. But that's the basic situation. Now let's pick a particle size. Mine is, well, let's say this is a sluice box, and you're running 2-inch material. So let's say this is 2-inch. Okay? Come up here, here's your 2-inch silica, and then come over here, and this is the kind of gold, that's the size gold that is relatively easy to extract. This is probably going to be somewhere in the neighborhood of, I don't know, 50 mesh, 50 to 30 mesh, somewhere in there. It's going to settle at basically the same speeds, and therefore that's what you're going to be able to extract reasonably well. Once it starts getting smaller than that, you're going to start getting substantial losses. Anything bigger, you've pretty much got it all. Now, what you can do at this point is you can screen your tank. Let's suppose you still had a lot of gold out here. A lot of fine gold in here. Maybe most of it's in this area. Okay? Screen it. And that's like 30 mesh, so call this 20 mesh. Now it's going to come over here and get that. Maybe we need to go 30, 50 mesh here. Oh, that looks much better. If that doesn't get it, then do it again. This may be, oh, let's just say 150 mesh. Okay? Now you're going to get all the gold, basically. When you make your first cut, your first classification before you put it in the process, that determines your initial top size. In plasters, that can be fairly large. You may be running 1 or 2 inch material through your sluices. That's determined by how big your largest expected nugget is going to be. And the one that's going to occur at any reasonable period of time. Yes, you're always likely, you can reject a nugget. What they've done in a situation like this is they'll put a trap door on the output. You got like a conveyor, and it's dumping, and there's a little slide there. It has a trap door in it, and there's a metal detector. And so if anything comes up and is sliding down that slide and cause that metal detector to trip, that trap door opens up, and you catch it. Whether it's artifacts, gold nuggets, whatever, you don't lose it. But you don't have to process everything. You just have to run it over that chute and under that metal detector. So many plasters, you may be doing 1 or 2 inch, big trommel or whatever. You may classify it down to 1/2 inch. Okay? If your initial top size is 1/2 inch, you're doing a little better. But anyhow, do your initial top size, whatever it is. I'm crushing rock. I need to get mineral liberation. That means I'm probably going to have to crush it 20 to 50 mesh minimum. My standard screen for the input side of my extraction table is 30 mesh. Anything over 30 mesh goes back for a regrind. I keep regrinding that. At the end of the day, I'll keep regrinding it, running it over the table until I get a small enough amount to pan, then I'll hand pan it. If there's any gold too big to go through the screen, I'll get it then. If there's a really big nugget, it's going to get mashed in the rolls crusher, and you're going to see this big giant shiny thing like that. But anyhow, this is essentially how you do it. You determine your initial top size based on ore parameters, such as if it's placer, what's the largest economically likely nugget you're going to see. That's where you screen it to your top size. Then you actually examine your tailings and see what size gold you have. Let's suppose that you had, and let's put it right here. You got your 2 inch top size And this is all the gold you see in your tailings. All this stuff out here is basically clean. Right about here is where you would want to do your initial screen. And then all you're going to lose is that. So in a two-step process, from 2-inch to say 100 mesh is your first material. You know, 2-inch minus, you're going to get everything down to 100 mesh gold. Sorry, you screen it before throwing it away to 100 mesh minus. You throw away the 100 mesh plus and then redo the 100 mesh minus. In reality, this curve isn't too representative reality to a 100 mesh screen size. You should be able to get down to 300 mesh gold without too much trouble, maybe 400. And this brings us up to another thing, is what kind of secondary processing do you use? A real simple thing for placer is something called an undercurrent sluice. So let's draw a sluice box here. You have a standard sluice box. It's got some kind of riffles, some kind of matting. And let's say this is from a previous example. This is 2-inch coming in here. And you're getting everything down to 100 mesh gold. And now you want to screen it. You got 2-inch rocks, so real fine screen is going to be a bit of a problem, but you can screen it even better. You do is you put a piece of punch plate here. Punch plate is that metal sheet with a whole bunch of holes punched in it, and you get various sizes and such. If say you had punch plate with 1/8-inch holes, you think, I'm going to get 1/8 inch minus out of that. Well, technically yes, but you're going to get very little around the 1/8 inch, because if here's your punch plate, like this, and let's see, that's about the size of the holes. As this particle comes down here, it's going to go bang, bang, bang. It's not going to make it through. You got a fairly good flow rate here, so the larger particles are going to bounce off of the plate around the holes. They're not going to get sucked into easily. So it's going to take a much smaller particle to reliably go through the hole. If this is an 1/8 inch, you might get 30, 40, 50 mesh will be your actual top size. In addition, since you're talking 100 mesh gold is what you're really looking for, those particles are going to tend to be riding close to the bottom, and they're going to easily go through these holes. So you should get the vast majority of the gold going through there, and the silica is going to be, you know, half the size of the hole or less. So that's the nice thing about an undercurrent sluice. Then you take this material and you can run it over a jig, or you can run it over another sluice that is much slower and finer. You know, maybe something like with hog mat, or you know, one of these new mats. It's a very, just a series of real small riffles in the mat itself. I've heard they get recoveries down to 300 or 400 mesh, and they have river sluices that actually have undercurrents built into them now, some of the larger ones, that use this exact principle. Now, I'm dealing with hard rock gold, and hard rock gold has even finer gold than that. So I'm starting at 30 mesh due to mineral liberation. I'm running it over an extraction, and if I'm losing a fair amount of real microfine gold, which so far I'm not, I can do a couple of things. Let's see my process here. I've got a table. Comes off the table, hits a screen. My final output screen is a 90 mesh screen. So what comes in the water here is, I'll just call it 100 minus. It's probably smaller than that. And then this is dewatered tailings. Okay, I know I'm getting all the 100 mesh. That's not a problem. I'm actually getting down to 250 mesh. That's the smallest that I'm basically seeing. Now, that may be the smallest there is. That's also the smallest I'm seeing in my pan. And this is where it's really handy to be able to do that panning microfine gold technique. You can assay rock, and that'll tell you how much is in it, but it doesn't tell you in what form or in what shape. By doing the hand panning, or there's something called small plate amalgamation, whatever, you want to recover the gold in its original form. So you can see the size and the shape of the particles, because that drastically affects how you can extract it. So let's suppose I'm losing a lot in this 100 mesh minus, and it's 200 mesh gold. Well, see, it's already screened for another process. I could take this, potentially just retable it, if there was enough to make it worthwhile. I can take this right here and take something like this and pump it in here, and most water comes out there. And by determining the size and the speed of the water flow across here, most of the silica particles will come across here. Your slimes, your clays, the things that are really easy suspended come over here, and only the heavier particles drop down in there, and then you put a valve here to drain it. This is called a thickener. And in theory, you can design a thickener that will catch the gold and reduce some of the other stuff, especially the real fine slimes that are just a pain in the butt for filtering, leaching, everything. Now, at this point here, if you could gravity that out, that's fine. If not, you might just take that and leach it. Again, it depends on how much is in there. There's something called a pinch sluice. This is an interesting little device. It's a concentrator. Very simple. You have a sluice. Come on. It basically comes to a narrow point here. And you feed finely classified material up here, and it flows down the sluice. It's fairly gentle, but enough to keep it moving. And if you look on the side, what will happen is all this stuff here is mixed, and it'll tend to segregate into layers. Your gold's going to be on the bottom, then there's going to be black sand, then here's your silica, and at the end here you have a splitter. You have this like right there, where that goes down and this goes somewhere else. And so you can make a concentrate. Now this is not going to give you clean gold by any stretch of the imagination, but again, it concentrates it. If you get a 5-to-1 or 10-to-1 concentration, that may take you up to the point where it makes it real easy to leach. Leaching is expensive, often using toxic chemicals and stuff, and it has residence time. You got to put it in there and you got to take your time leaching it. Depending upon the particular leaching solutions, it can be much more rapid than others, but there's always a residence time, etc. The more crap you can get out of there before you leach it, the better. So again, you can concentrate. There's lots of jigs. Classification improves the concentration process. And you can do a primary concentration, a classification, a secondary concentration, maybe even a third classification and a tertiary concentration. They can be the same kind of device in series, like an undercurrent sluice, or you could have like an undercurrent sluice going to a jig. You know, you could have the jig concentrates going to a table, all kinds of possibilities. But I just wanted to bring that to your attention. What you do is classify it to where your device is going to work well. And that's how you classify it. The top size, the initial top size, determined by either mineral liberation or what's the largest gold particles you're willing to throw away. That's your first one. Then in a placer, you're typically going to have more stages if you've got a lot of really fine gold, which you tend not to have. You tend to have, you can have a lot of fine gold in placer, but not usually the micro fine gold, you know. So you just screen and check and use the panning technique to see what you're missing. Now you can combine that with assays to tell you how much you're missing, especially if you're, you know, dealing with really micro fine gold. You may have a problem actually recovering it with the pan, but that'll give you an idea how to go real quick, because you'll get to know the particle size. How do you know the particle size? Real simple, you can use one of these. Now this costs about 40 bucks. It's a 40 power hand microscope, and it has a reticle in it. In other words, when you look at it, you actually have a scale in your field of view. And how that works, if here's your field of view, here's your scale. And you just take your particle, move it around to where you can see it, and just directly measure it, just like laying a tape measure up against something. It's essentially that simple. 35 bucks. I think this morning it was $35. I was looking on the internet, but roughly 40 bucks. And with a 40 power microscope, it also allows you to see a little more detail of your gold particles than you would under a simple loupe. Oh, and here's one other kind of concentrator that I've heard sometimes works real well. It's called an elutriation column. Basically what you have a pipe with another pipe in the side, and this goes off, and this has a collection thing, and it also has to have an inlet. Now water comes in here. There's usually some kind of device here to stabilize the flow, to turn it from a turbulent flow to a laminar flow. Very, very smooth upwelling coming up here. And then here's where you put your slurry. So it comes in here, and by adjusting the speed of this, you can theoretically wash the lighter particles up while the heavier particles settle down and wind up down here. That's called elutriation. And again, it's just another form of concentrator. Sometimes these might work very, very well, especially on a tightly classified material. If, say, you've got 200 mesh gold and 100 mesh silica, theoretically this would not be too hard to adjust. So those are some ideas, those are some principles you can apply to your particular process, and don't be afraid to screen it, try it, pan it, see what's happening. Don't assume everything's working right, because quite often it doesn't. Cars need to be tuned, lots of things need to be adjusted, so do mining processes. So, happy prospecting, and keep it safe out there.